So the last time we talked about these radical reactions. We talked about the initiation, propagation, and termination steps, and the mechanism and abstraction happens in propagation, and then you can combine radicals and the products and termination to make the products. One thing we didn't talk about when we were talking about the termination steps is one of the reasons why this is not a I don't want to say not a widely used process, but why it's kind of sometimes you avoid using the radical process, and the reason is because sometimes your radicals can combine in ways you don't want, right? So let me show you that, and then we're gonna jump down here and do these percentages, and yeah, that's gonna be that. So let's say, let me add a page right here right quick. And then I just wanna kind of point this out. So let's say I have these two radicals like this. Let me make sure I draw the right thing. Yeah. So I had this radical with a radical here on this carbon. Right? The electron just ain't cooperating. And then I had this radical with a radical on this carbon. And then I had this radical with a radical here. Right? So what happens sometimes is what we call disproportionation. It's a big word, but it's not that intimidating. So we have what's called disproportionation. That's when your radicals let me reword that. Your radicals from propagation combine. Right? And so with this disproportionation, what happens is you get all kinds of like different products that you don't want, right? Unwanted products. If we're trying to do radical substitution and we're trying to add a chlorine to the radical, we don't want these radicals to start mixing together and giving you all these weird alkyl chain products. Like say, for instance, if I took this radical and mixed them together, right? Then I'm going to get this product, right? And I don't want that. I'll get a product like that, a 10 carbon chain. That's not the goal of the reaction, right? It's by the same token. If this radical here combined, let me move this down. I don't want to get mixed in. If this radical combined with another mole of itself, right? I don't want this product. Right? I don't want that product. And the reason I don't want it is because that's not the goal of the reaction. The goal of the reaction was to do radical substitution and put chlorine on the chain. Get this chain together, get my life together. Right? I don't want that product. And by the same token, if I took this and that, I'm just showing the radicals combining with themselves, but they can mix and combine any kind of way, right? And that really poses a problem because what you end up getting is a bunch of stuff that you, right? You get a bunch of products that you don't want. All of these products come from what we call disproportionation, right? So you get radicals that combine with each other, the ones that you made in propagation that's supposed to be substituting, they end up reacting with each other, right? So that's one of the drawbacks of doing radical substitution. Right? It's a drawback because you get a whole bunch of different stuff that you hadn't intended, right? And there's really no way to stop it. That's why it's called a radical chain reaction. Once it starts, it's like it's done. There's nothing you can do to really control the product outcomes, right? The only thing that really that works in your favor is that sometimes these disproportionation products are they're less stable than alkyl halide products that you get. All right. So that's a big drawback. So that's why this process is not always widely used. So let's jump in now and let's talk about, hopefully you watched that video too. At least you'll have a little bit of a foundation to work from when we start talking about this. So let's talk about predicting a product distribution. So let me put that up here as a heading. I'm going to abbreviate. Anytime you see me write product PDT, it's just an abbreviation. Can somebody tell me what the definition of product distribution is? I think I gave it to you on Monday. You can unmute yourself and say it. That's fine. Don't be scared.
What'd you say again?
Is it the ratio of products?
Product distribution. Go ahead. I think that was you, Amari.
Oh yeah, I said, is it just the ratio of products?
Just the ratio, right? It's a big fancy term, but all it means is the ratio of the products that you get from a particular reaction, right? And so with these radical reactions, what we got to understand is that these are competitive processes, right? So that termination to make those three products, that's a competitive process. And because it's competitive, and because you make radicals, some of your radicals may be more or less stable than the others, that's gonna, what that leads to is varying ratios of products being formed. All right, so there's a way to calculate the product distribution for a radical reaction. So I'm gonna draw the products back down here. So I'm gonna draw the whole reaction. I'm not gonna draw the mechanism, just the reaction. Right, so we started out with this. Sorry about that. Come on, Russell, get your life together now. I'm gonna slap this iPad. If y'all hear it break, you'll know class is over. So I'm gonna start out here. We started with this pentane. We treated it with chlorine, right? And we shine light on it, and we get three products out. All right, we get this product, and then plus that, and then plus that product. Let me fix that up a little better. All right, so those are my three products. All right, the main point of this exercise is, well, we got 2 points that we're trying to point out. We want to figure out how much of each one of those we're going to get, and what the only skill you need is to know the difference in a primary, secondary, or tertiary carbon. If you know that, the equation part is it's just plug and play. Let's see. All right, can you hear me now?
Yes, we can hear you. It's just like breaking up
All right.
here and there.
Yeah, so again, what the skills that we're looking at here is being able to identify primary, secondary, and tertiary carbons. And from that, we're going to use that information to plug in the numbers into this equation. So let me explain what this equation is. So this is one number right here, right? That part of the equation is the number of hydrogens. The I is just telling what is primary, secondary, tertiary. And then R, different color, sorry about that. R is going to be the reactivity factor. That's my reactivity factor. That's a given number. There's no guesswork in that, right? I got a chart right here that talks about the reactivity factor for bromine and for chlorine, because those are your two most common halogens used for substitution, right? So that's my reactivity factor. And again, it changes based on the type of carbon, primary, secondary, tertiary. Big difference. The reactivity factor goes up for tertiary carbons because those carbons are more stable as radicals, right? Let me rehash that. So if you have a carbon, I'm just gonna write all of these out. And then, so this is a methyl. And then this would be an example of a primary. Hold up. All right, so methyl, primary, secondary. Let me highlight the carbon we're talking about. So we're talking about this carbon right here. All right, so methyl, primary, secondary, and tertiary. In terms of carbocation, so if that carbon had a plus charge on it, let me just see if I can. Right, in terms of carbocations, this would be, the methyl would be the worst. And then the tertiary would be the best. All right, methyl would be the worst, tertiary for cations, and radicals follow that same pattern. All right, so let me put that on this side. Same pattern. Cations are methyl is the worst, tertiary is the best. Radicals, same thing, right? Because a radical, let me show you that on the, let me go to another page here. Let's say I'll have a tertiary radical, right? So this is a carbon, and I'm going to put 3 CH3 groups around it. And 1 electron, because remember, a radical has a single unpaired electron, right? What that actually is, that radical is actually in a p orbital, right? It's a half-filled p orbital. Right, so you got 1 electron in that p orbital. Let me fix that carbon too. All right. And so when you have a tertiary carbon like this one, or a tertiary carbocation, this is why the tertiary right? That's also in a p orbital, but it's just empty, right? So this is why the tertiary carbocation, tertiary radical are so good or so stable, because that tertiary carbocation and tertiary radical, those carbon-carbon bonds adjacent to it, right here, they're all pumping electron density towards it, right? So those dipoles are going to be towards the radical or towards the carbocation. Same thing down here. Right? And so when that happens, it stabilizes the charge or it stabilizes that half-filled orbital, right? That term, there's a term for that, is called hyperconjugation. Big word, but we're not intimidated by big words. Right? All that means is inductive stabilization by carbon-carbon bonds. That's it. So you got all these carbon-carbon bonds around your charge or your radical, and they're pushing electron density towards that p orbital, and they stabilize that radical or that carbocation through induction. All right. Any questions about that? So let's think about that in terms of, what if I had an anion? What do you think if the charge was negative on carbon? What do you think? Is it going to be more or less stable? Is it going to follow the same trend, you think, or is it going to follow? It's going to do something different for anions. So cations and radicals both follow the same trend. Methyl is worse, tertiary is the best. What do you think about an anion?
I think it's opposite for anions.
It's going to be the opposite, right? Because if an anion, let me draw that out. I got room down here. I had to zoom in some on this screen. So if I had an anion, which is a negatively charged atom, right? So if I have a carb anion like that, and I put a bunch of methyl groups around it, this is bad, right? Because you already have a charge, and this is already electron rich. Right? So because it's electron rich, it does not want a bunch of electrons around it. So a tertiary anion is the absolute worst anion that you can make. Right? It's a very bad situation, very unstable. Right? So the anions follow the opposite trend. Right? Tertiary is the worst, methyl is the best. So I'm gonna write that. I'm not gonna write out a whole chart, but I'll just write it like this. So methyl is the best, followed by primary, secondary, and then tertiary. All right. So that's important to think about when we talk about these radical reactions and why the reactivity factors change from primary to secondary to tertiary, is because those radicals that you make on those primary, secondary, tertiary carbons are going to be either more or less stable, right? And when that happens, that means that some are going to be more reactive or less reactive, right? So let's go back up here to the example right here, all right? And let's see if we can figure out, I think I want to cut this. Let's see. No, it ain't gonna take all of that. So let's cut this out. And then we're gonna go down to the next, to another a clean page and work through the percentages. All right. Nope, that's not gonna work. Hold up. That's just gonna try to copy all this stuff too. I'll rewrite that down on the other side, don't worry. All right. So we'll go here and I'm gonna paste it. Blow it up. All right. So here's my chart. Again, here's the reaction. I have pentane reacting right? And from that, I got 3 products. This is one, this is the other again, and then that's one. All right, so how do we figure out which one of these, the percentages of these? Let's do that. So we know all about primary, secondary, tertiary. We know all that good stuff. All right, so let's figure this out. Again, let me get that equation right quick because I don't think I copied that part. All right, so that's my equation. And again, the NHI is the type of proton. That's primary, secondary, tertiary. R is a reactivity factor. All right, so let's see if we can figure out how much of, well, let's see if we can figure out the number for this product right here, right? Because that's on a primary carbon. Okay, I want to take you back to when we first started this problem. How many primary hydrogens are present in pentane? So let's look here. This is pentane right here. How many primary hydrogens are present?
2.
How many?
2.
No, that's the, okay, so primary carbons, yes, there are 2
Oh,
carbons.
carbons.
How many hydrogens are on each carbon?
3. So
there's a total of how many primary hydrogens?
6.
6. Good, good, good. I think you got it. You with me? We got 6. And with this, when you're doing this process, you got to account for all of the primary hydrogens, even though we only showed one side reacting. Because remember, when we first started doing this, we said that there was some symmetry. And because of the symmetry, we don't have to show both sides. We only show one side. But when it reacts, it's really important to understand it can react from either side, right? So you got to include all those hydrogens. So for primary, you got 6 hydrogens. What about secondary? These are your so you got 3 secondary sites. But remember, we said that 2 of them were the same, right? Here and here, and then 1 of them was different. Is that right? Do y'all remember that?
Yeah.
So we could do it. I want to break them apart. I don't want to combine them because I want to be able to say with specificity how much of this product I get right here, right? Versus this product. So I'm going to break them apart. So we got secondary carbons or secondary hydrogens, and I'm going to break that up into 2 and then 4. But there's a total of 6. If you don't want, if it's not specific, then you can lump them all together. But because you got 2 different types of sites, even though they're both secondary, they're going to give you different products. So we're going to break them apart. So is everybody okay with the fact that there are and we did this the other day, but I'm gonna repeat it. There's 2 hydrogens here and 2 here. So that's a total of 4. Are y'all with me on that?
Yep.
So I'm gonna highlight that. So that's the 4 right here, the pink ones. And then the blue here, right? We following that? So we got 2 hydrogens at that site that's highlighted in blue. Yes or no?
Yes.
All right. And then the halogen that we're using is chlorine, right? So the reactivity factors we use are, shucks, didn't try to do that. The reactivity factors that we use are going to be for chlorine. All right, so up here, we're going to use this set of reactivity factors right here. So for primary, R is going to be 1. For secondary, R is going to be 3.9. The tertiary is going to be 5.2. All right, so let's jump right in. We're going to calculate the bottom. This is the way I always teach this, is to do the bottom first. What's the sigma stand for? Anybody?
Summation.
It's a sum, right? So you're going to take each one of those pieces and add them all together. Once you do that, you don't have to do it again. All right. So now let's take, for the bottom, we're going to take the sum. So for the primary, we got 6 primary hydrogens times a reactivity factor of 1. This is NHI. This is R. It's that simple, right? Don't let the N and the H and all that stuff fool you or intimidate you. N is just the number of number. H is the hydrogens. I delineates the type: primary, secondary, tertiary, right? So NH for primary is 6, and then R is 1. And then we're going to take that, and then we're going to take the secondary, one of them. So we're going to do the 4 first. 4 times 3.9, and then plus 2 times 3.9. Anybody not see what I just did or not understand? And so this is going to be my sum. I'm going to sum all of these up. Is that okay? If you don't see it, say something.
Yep.
All right. So that's 6 plus 7.8, and that's be 7.8, 15.6. Is that right?
Yep.
All right. So 6 and 7.8 is 13.8, and 15.6 is 29.4. Is that right? So when I sum these up, I get 29.4. There's no units, right? All we do, these are just numbers, no units. So you don't even have to keep track of units. So that's the sum. And then when I want to figure out how much of each product I'm going to get, I plug it into the equation. So let's say for primary, let's say the primary. What color did I have there? Orange. For the primary, let's say that. So in that equation, it's going to be 100, because we're doing percentages, times, come on, Russell. All right, I'm just going to write it out, NHI times R over the sum of NHI times R. It looks intimidating, but it's really not that big of a deal. So if I want to do the primary, I'm going to do 100 times 6 over 29.4. Is that right? Because I've already calculated the NHI times R for the primary. It's 6 times 1. 6 is the NH part. the R reactivity factor is 1. Is that right?
Yeah.
Yes.
Okay. So I don't have a calculator for that, but it's going to be somewhere around 20%, because 1/5 of 30 is 6. So 6 divided by that would be somewhere around, am I right? About 20%, 19%?
Yeah.
All right,
20.
it's 20%?
Yes, sir. 20.4.
Okay, so 20, come on, man. 20.4%. So out of all those 3 products, 20% of that is going to be this. Right, 20.4%. Let's do the other one. We already got the sum, 29.4, so we don't have to do that again. We just need to plug the numbers in. So we're going to say 100 times, what is it, 7.8. Let's do the 4 one, 15.6. 15.6 divided by 29.4. That's going to be close to 50%. Somebody hit me with that right quick. A little bit over 50%.
53.1.
Okay, so 53.1%. Good. Thank you. So that second product, this one, is going to be 50, sorry about that, 53.1%. All right. I'm trying to write with this stylus and keep my palm off my screen, and it just ain't working. Let me use my finger. 0.1%. All right. Now, what about the last one? What is that going to be? 7.8.
26. Oh, yeah.
Mm-hmm.
Yeah, the answer is 26.5.
Okay, good. So 100 times 7.8 over 29.4. You said, what is it now? What did you say? 26.5.
5.
Okay, cool. So 26.5%. Obviously, it's got to add up to 100. If it's greater than 100, you did something wrong. Right? All right, so 26.5% for the other secondary product, which is this one. All right. Any questions about that? All right, I think the example in the video was a lot more difficult because you didn't have that symmetry, so you had to calculate everything. But it's a tedious process, but it's not impossible, right? It's just a matter of knowing what you're looking for, right? So if a problem asks you to calculate the product distribution for monochlorinated products or monobrominated products, whatever, you'll know how to do that. It's just a matter of knowing what you're looking for. You got all the tools you need. You know what a primary, secondary, tertiary carbon is. If you don't know that, that's something you got to brush up on to make sure that that's part of your skill set. And that's something we've already talked about multiple times. All right. And then the equation is just a matter of plugging numbers in. And again, you got to take all of your hydrogens into account when you're doing this equation. Even if it's symmetrical, you still have to add up all of your primaries, all of your secondaries, all your, tertiaries or whatever. All right. Any questions about anything? All right. Let's do another example. And we're going to probably run out of time, but I want to do another example. I want to give you some time to work and see what you do, what you're able to do. So we're gonna take let's work through this example. All right, I got it. Okay, so monobrominated products. How many products are you going to expect? Let's get that out of the way first. Because once we do that, then it kind of helps us guide us through the process. So what do you think? Is there any symmetry here? Besides these two carbons, is there any symmetry?
No.
No. All right, so you're gonna have, I'm gonna highlight the carbons and I'm gonna see what you got. I probably should do a different color instead of purple out here. I'll do brown. Right, so one of the things that you have to look out for when you're doing these types of problems is like these isopropyl type groups, like what's shown out here. I'm gonna just circle it. All right, these two carbons, this one and this one, they're the same. And the way you know that is if you take one of the hydrogens off and put a chlorine or a bromine there and name the compound, you're gonna get the exact same thing, right? So those will be identical. So when you're adding them up, when you're adding them up in the sum, you add them up as a second set of primaries. But in the product, you're only going to see one of those products. It's up to you which one you want to use. All right. So let's draw the products out. Right. Where will I get a bromine in this molecule? It's kind of a trick question, but kind of not.
So the bromine replaces.
Yeah, we're doing a radical substitution, right? So what sites am I going to brominate? Because you can predict the products without going through the mechanism, even though we are going to go through the mechanism. Wouldn't every site that's a different color get brominated?
Yeah.
That's why we picked them out first, right? There's no symmetry. So for this substitution, every site that's not the same is going to get brominated. Right? So my products, I'll get I'm just going to read.
So would you have 4 products?
Yes, 4 products, because 2 of those sites are identical. That's exactly right. So I'm going to have this as a product. I'm going to have this as a product, and it'll be plus that. And then I'll get plus that as a product, and then plus I'm just going to put it down here, plus that. Come on, laptop. Let me make sure I get this drawn properly. All right, are we following that? So you're going to get 4 different products, again, because the two carbons highlighted in brown are identical, so you only need to worry about one of those as it relates to product formation. when you get ready to sum up and calculate the percentages, then you take both of those into account. Anybody not see what happened or what I did? Actually, I'm gonna move this bromine.
Okay, I get it.
All right, I'm gonna put that bromine out here instead of pointing it down. All right. Any questions about that? Those are my 4 products. How do I make them? That's the question. What are the 3 steps in any radical mechanism? What?
Initiation, propagation, and
Propagation,
termination.
termination.
Good. Those 3 steps are for every radical mechanism. All right. Every radical mechanism. The initiation step is going to be bromine getting broken up into its 2 parts. Excuse me. Right. Let me put the electrons around here. So I want to break this in half, right? I'm going to shine light on it. What type of bond breaking is that again?
Heterolytic.
It can't be hetero because I'm using one electron. It's homo.
Homolytic.
Right. So I get this plus this. Is that right? That's my initiation step. And then in propagation, what's going to happen? What's the term I gave y'all for what happens in propagation?
Abstraction.
Good, abstraction. So every one of those sites that's different, that has a different color, is going to get abstracted. And so what I'm going to do is I want you to show me the abstraction steps, and I'm going to make this an extra credit. So for the 29 people who are here, we're gonna make this an extra credit for you to show me the propagation steps. So every one of these carbons, I'm gonna zoom in because I'm gonna write these hydrogens in, right? So this is a come on, man. This is a CH3, right? This is a CH2. This is a CH because it's tertiary, and then these are both CH3s. Right, so those are all your sites that are going to get it. But keep in mind, for the ones highlighted in brown, you only need to pick one. It's up to you which one you pick, which site, because they're identical. Right, so that's where all your abstraction steps are going to happen on those carbons. And then what's the final step? Anybody?
Termination.
Termination, right? And then termination, that's where all your products get made. I'm going to move this over and make some room. So let me erase this. I'm gonna move this product over. All right, so all of this is this plus that, and then plus that. So you get 4 different products. Let me show you the first propagation step, and then for the extra credit, I want you to show me the rest of them, plus termination. All right, because this means absolutely nothing until you put pen to paper and do it yourself. Because when you get on the test, you're gonna have to do it yourself. So let's take, I'm gonna cheat for a second and just see if I can copy this thing and paste it. Do me right now. Copy that. Come on. Y'all keep your fingers crossed. You know, this technology, sometimes it works, sometimes it doesn't. That time it worked. All right, so in propagation, let me put a little line right here to separate these. So in propagation, what's gonna happen? This is the first propagation step. And I'm gonna pick this CH3 down here on this end. What am I reacting this molecule with in propagation?
Radical, the bromine with the radical.
Br dot. Good. Excellent. Right? That's what I'm reacting it with. And how do I show the reaction? How do I show it happening? If I wanted to react the terminal carbon down here, how would I show it?
You have your arrow going.
Let's take this one down here just for clarity, because it's easier to see and easier to get to. So we want to do this, right? Is that right?
Yeah.
Okay, so that is going to mean that this H and Br are going to come together on the opposite side, in the product side, and then I'm going to leave one electron on carbon. So let's draw out what that radical would look like, and then we're going to stop, and then I want you to do the rest of them, and I'm gonna put a link in Blackboard for you to post it by tomorrow, and put your names in the chat box too, because if somebody is not here, they're not getting the extra credit. All right. If another scammer calls me, y'all gonna hear me cuss, but don't tell nobody. Okay. All right. So here we go. So here's what that radical should look like. So this is a CH2 now with one electron on it. Anybody not see that? So after that propagation step, that's what I get. And I'm going to do that on each one of those carbons in the chain. So I should get 4 radicals in propagation. It's up to you which one of these you do, here or here. You pick. So I want you to show me the rest of the propagation steps. Use the right arrows. Don't use double-sided arrows. Use fish hooks or single-headed arrows. Not double-sided, double-headed, I'm sorry. And then I want you to show me the rest of the propagation, and I want you to show me the rest, the termination steps, to put bromine at each one of those sites. All right? And make sure you put your name in that chat box, because if I don't see your name, but I see an assignment, you're not gonna get credit for it. All right? So fill up the chat box. All right, any questions about anything we've done so far? This is not a lot. It's not hard, it's just tedious. It's very tedious doing these radical mechanisms. But it's not a difficult process at all. Right now I'm showing 29 people logged in, so there should be 29 names in the chat box. All right, any questions? All right. Right, let me zoom out just in case somebody's still writing that down. All right, so today what we talked about is we talked about calculating the percentages, the product percentages or product distribution of a radical substitution. We talked about the types of carbons, primary, secondary, tertiary, and methyl. And we talked about the stability trends between radicals, cations, and anions, right? If I were you, I would put that somewhere and hold on to it, the stability trends, because you're going to see that again when we get to the next section, I think. When we're dealing with alkenes, you're going to see that again. And it's going to be very important to understand that those stability trends, to understand how those alkenes react. All right? Is everybody's name in the chat? Let me see. I'm not going to count them. I'm just, when I end the meeting, if it's there, it's there. If it's not, it's not. But make sure you put your name in there so when I post the extra credit, you can get credit for it. All right. I'm going to stop recording. Did I stop recording? Yeah, let me stop.